For the next part of our course, we're going to look at aspects of the construction of lithium batteries and the materials that are used as anodes and cathodes and the characteristics that they need to have to optimize the performance. So let's start with cathodes, and there are several different ones that can be used, but we'll look at the cathodes with the so-called layered rock salt structure. Rock salt is sodium chloride, NaCl, and many oxides have the same structure. For instance, magnesium oxide, MgO. And what the structure is a cubic close-packed layer of oxide ions with the cations in octahedral sites. So the cation-anion ratio is 1:1. And there are a family of more complex oxides with similar structures, and LiCoO2 is one of those, and it's really the parent structure of lithium batteries. Formula LiCoO2, so again, one cation to one anion ratio, so two cations LiCO, two oxygens. So again, it's cubic close-packed oxide layers and octahedral cations. But in this case, the cations fully occupy alternate layers. And as the diagram here shows, the oxygens are the brown color layers, and then we've got alternate layers of blue and purple, which represent our two types of cations. And so we can clearly see there that we've got a layered structure, and it's the lithium layers that are emptied and replenished during the charge-discharge process. So at the top we have an equation here, which we've had this one before. It represents the reaction during charging. So you take LiCoO2, remove a number of lithium ions X and a number of electrons, giving LiXCoO2, and as we said earlier, X is variable between 0 and 0.5. Another consequence of the variable lithium content is that the cobalt has a mixed valence of cobalt 3 plus and cobalt 4 plus, and this gives rise to increased electronic conductivity, because electrons in the d orbitals, chemists know these as the T2G d orbitals. If you're not a chemist, it doesn't really matter too much, but the d orbitals on adjacent cobalt ions overlap. These d orbitals are partially occupied, and electrons can easily transfer from one cobalt to another one, and this is facilitated especially if we have a mixed valence of cobalt. So that's how the electronic conductivity occurs, electrons hopping between cobalt 3 plus and cobalt 4 plus ions. So in utilizing this as the cathode, there are some general problems. 4 are listed here. First of all, slow diffusion rates in the solid state. So lithium ions don't move particularly quickly, not as quickly as they do in a liquid electrolyte. Secondly, this gives rise to low ionic conductivity, but also the electronic conductivity is not particularly high, especially when the material is fully discharged and just contains cobalt 3 plus. A third problem that occurs is very frequently there is mixing between the lithium and the cobalt layers. They don't stay entirely separate, and so there is some cation mixing during charge-discharge or during synthesis, and this can lead to a reduction in capacity and performance. And the fourth problem is that many of these materials, lithium cobalt oxide is okay, but some of the other layered rock salts lose oxygen at high temperatures, and this has an effect on the oxidation state of the cations and can have quite a dramatic effect on the voltage profile of the materials when it's used as a cathode during charge-discharge. So metallurgists, of course, are very familiar with processing problems in metals and how properties, especially mechanical properties, vary hugely as a consequence of the heat treatment of the metals. And although we are talking here about oxide powders, the electrical properties and the electrochemical properties can vary enormously depending upon the processing conditions, as we'll see later. So to treat these four problems, first of all, diffusion is slow, especially in the solid state. And let's do a simple calculation to illustrate this. And we can estimate the time that is required for a lithium ion to diffuse a certain distance if we know the diffusion coefficient of lithium ions in the solid. And a typical diffusion coefficient is listed here, 10 to the minus 10 square centimeters per second. So that's a typical value for hopping of lithium ions in a solid structure where there is some lithium ion conductivity. So if we do a calculation for a diffusion distance of 100 microns, which is the typical size of a grain in a well-sintered ceramic, and using the equation for the time to travel that distance, the equation is given here, T, time, is L squared over D. Then simply substituting L and D into that equation, and you can do that, then we get an answer of 10 to the 6 seconds, or 280 hours. So it'll take 280 hours for a lithium ion typically to diffuse from one side of a grain to another, which is not very good if this is the rate limiting step in the charge-discharge process of your battery. If instead we work with nano-sized particles and say, well, if we have a grain size of 100 nanometers, then the time required to carry that same diffusion process is 1 second. And so the conclusion from this simple calculation is that we need nano-sized particles of the redox active material. And since the redox reactions occur at the surface, we want a surface area that's as high as possible with nano-sized particles. So this is just the opposite of having nice, dense, sintered ceramics with low porosity. So we want high porosity materials and small particle sizes. And in practice, composite electrodes are used to facilitate these microstructural characteristics. And the next slide shows a typical composite electrode. At the top there we have the orange spheres are our redox active particles, and in order to facilitate electronic conduction, these are usually coated with a thin layer of conducting carbon, or the so-called carbon black, and that allows electrons to get readily through the structure from one particle to another and to contact with the outer electrodes. So that's one way of facilitating the electronic conduction. In order to increase the surface area of contact between the redox active electrodes and the electrolyte, which is usually a liquid, is allowed to diffuse into the porous composite and fill all of the gaps between the redox active particles. And so by this way of having high surface area, a composite of electrolyte and electrode, and electrode particles coated with conducting graphite, then we can get much higher rates of charge and discharge. One consequence of that, though, is that there is a trade-off between achieving rapid kinetics of the charge-discharge processes and the energy density that one can get from the battery. So the diagram at the bottom right shows schematically the discharge profile against time for our battery. So we have voltage as the vertical axis, voltage or quantity of electricity passed, it depends what we're plotting, against time. And you can see that schematically we're showing a slow and a fast discharge profile. And for a fast discharge profile, it will occur obviously more rapidly, but the total charge that can be passed also will be significantly less than for a slow process. And so this will depend very much on the microstructure of the composite, whether or not we can have fast charge-discharge processes. So how can we enhance the conductivity of the cathodes? Because this is essential, because many of the electrode materials that are used as redox active cathodes are insulators in the discharge state, and so it's essential that we can increase their electronic conductivity. And there are maybe 4 ways in which this can be achieved. First of all, as we saw in the previous slide, coating of the particles with conducting carbon at least enables the particles to have their surfaces in contact with a good electronically conducting medium, and therefore a ready contact with the outer electrodes. The second way that this can be achieved is by generating mixed valency of our redox active species. And I'll show you the slide in a minute of how this is achieved with lithium cobalt oxide, because the objective there is to obtain a mixture of cobalt 3+ and cobalt 4+, giving enhanced conductivity. Another way of generating, and that is done by magnesium doping, as we'll see in a minute. Another way of generating mixed valency is by having oxygen non-stoichiometry. So if the material is oxygen deficient, then the loss of oxygen is balanced in charge by adjusting the valence or oxidation state of your redox active element. In this case, we have manganese 3+ and 4+ in the formula. And one way that this can be achieved is by quenching materials from high temperatures, because it's very common that at high temperatures materials do lose a little bit of oxygen, and there's a formula there for rutile, TiO2, which loses a tiny amount of oxygen at high temperatures, but it's sufficient to transform the material from being a nice white fully oxidized insulator to a grey or black semiconductor just by losing a tiny amount of oxygen. So these are various ways and strategies that can be used to enhance the electronic conductivity. However, it's not always good news when this happens, as I'll show you a little later, an example where it doesn't help and it can cause a problem for the electrochemical performance of the battery. So let's look at the electronic conductivity of lithium cobalt oxide. And one of the early problems, which in fact I was involved with about 15 years ago, was the question of the intrinsic electronic conductivity, which is low, and asking ourselves the question, can this conductivity be increased so as to avoid the necessity of adding a conducting carbon additive? Because it's fine to add the carbon coatings, but then that adds additional weight to the battery and effectively means that your capacity on a weight basis is reduced. So we have here a graph showing the log sigma, which is the electronic conductivity, plotted against reciprocal temperature, 1000/T, which is the Arrhenius plot, which is the usual way to plot conductivity data. So just to orient you with this graph, a value of 3.3 in 1000/T is about room temperature. So room temperature, 1000/T, 3.3 on the horizontal scale at the bottom. And then the conductivity values are shown here between 0 and -8. So 0 would correspond to a resistance of 1 ohm. And so this is the high conductivity. So for high conductivity at low temperatures, we're trying to get our materials up towards the top right corner of this diagram. And you can see here conductivity data of lithium cobalt oxide in 3 atmospheres: argon, oxygen, or 1% oxygen, and air. And the conductivity is much higher in air than it is in argon, especially at lower temperatures. And this tells us that because the conductivity is higher in an oxygen-rich atmosphere, that means that the conducting mechanism is p-type, which means it's a whole conduction mechanism, because from the little equation on the right-hand side, oxygen goes to oxide ions plus holes for charge balance if we increase the oxygen partial pressure by changing from argon to air. So we are creating holes as oxygen absorbs on the surface of the sample, and those holes are what are responsible for the conductivity. So from that graph we can say, well, if we want to increase the conductivity, we need to find a dopant that can increase the hole content. And thinking about lithium cobalt oxide, which contains cobalt 3+, that means that we want a dopant that can increase our cobalt 4+ content. And the next slide shows how that is achieved, and the magic dopant is magnesium. So magnesium 2+. Magnesium doesn't contribute anything to the redox performance because it's fixed as Mg2+. But if we substitute in the crystal lattice 2 cobalt ions with a charge 3+ by 1 magnesium and 1 cobalt 4+, then we have both mass balance because we've replaced 2 ions by 2 other ions, and we've got also charge balance because we've got 6+ with 2 cobalt 3+s and 6+ with a magnesium 2+ and a cobalt 4+. So effectively, by adding a small amount of magnesium to the lithium cobalt oxide, we are creating a mixed valence state of cobalt. And the diagram on the left shows the consequence of doing that, of replacing 5% of the cobalt by magnesium. And again, it's an Arrhenius plot, log conductivity against reciprocal temperature. And you can see the data for the undoped lithium cobalt oxide and then the doped lithium cobalt oxide. And the doped material, that particular material has a resistance approaching 1 reciprocal ohm centimeter. So it means it'll have a resistance of 2 or 3 ohms or 2 or 3 ohm centimeters, compared with a much lower value for undoped lithium cobalt oxide. So that's how we can modify electronic properties by doping. Next topic concerns oxygen non-stoichiometry and the quite common occurrence of oxygen deficiency in lithium cathode materials, which arises from the method that is used to manufacture them. So to make the lithium cobalt oxide, lithium manganese oxide, and so on phases, you react together lithium carbonate with the oxides of manganese and nickel and cobalt and so on, and then heat them at high temperatures to get into diffusion and to form your rock salt or spinel product. And then after that, cool the samples to room temperature. And if the samples are cooled quickly, it turns out that they are quite different frequently from those which are cooled slowly, because at high temperatures the materials are oxygen deficient, and if they are cooled slowly they have time to reabsorb oxygen, but if they're quenched instead then they remain as being oxygen deficient. So consequences of oxygen non-stoichiometry are that the transition metal oxidation state depends very much on the processing conditions, and in particular on the final cooling rate after synthesis. And this can have a significant influence on the cell potential, the voltage of the cell and its profile during charge-discharge. So it affects both the potential profile and also the magnitude of the capacity. So what we're seeing here is there's a direct link between the processing of the materials and their properties. The next slide shows a nice example of that. This is of an oxide. In fact, this is a spinel structure. Spinel has the general formula AB2O4, and so this spinel has Li, and then the transition metal is, which should be 2, is 1.5 manganese and 0.5 nickel, and then 4 oxygens. So AB2O4, but depending on how it's prepared, the oxygen content may be a little bit less than 4. And what the graph shows is how the potential of a cell using this as the cathode varies during the cycle of charge and discharge. This material was first synthesized maybe 15 years ago and was quite exciting because it's quite a high voltage cathode. You can see that most of the thick black line has a constant voltage of about 4.8 volts. And so this was an exciting material at the time, as one of the first cathodes that operated almost at 5 volts. But what you see there is, for the same material that was fabricated in different ways, the profile is quite different. So the thick line, it's called HOP, that's high oxygen pressure. So it was treated after synthesis in a high pressure oxygen furnace to make sure that the material was fully oxygenated, so delta equals 0. And that gave the very nice performance with a constant 4.8 volt plateau. However, material that was instead quenched from different temperatures showed quite a different performance depending on the quench temperature. And what in fact you see there is that there is still a bit of a plateau at 4.8 volts, but over much of the profile there is a second plateau at around about 4 volts. And this is because we now have different redox couples associated with the process. So the manganese oxidation state has changed from +4 to +3, and that is then giving us a different redox couple in the process. And so that is really quite bad news for the battery, because you want to have a constant voltage during charge and discharge. So the conclusion from this is that the potential profile on charge and discharge depends upon the oxygen content, and therefore illustrates the importance of materials processing to the subsequent performance. So, pursuing that a little bit further, do we know what the oxidation state of the different elements is? And there is a very nice technique which you won't have in your laboratories. You need the national facilities of synchrotron radiation to do this, but it's called the X-ray absorption near edge spectroscopy technique, or ZANES, or ZANES. And this is a way of determining the oxidation states of the particular elements in your material. So the basis of the ZANES technique, you're probably all familiar with X-ray diffraction and how X-rays are generated by intershell transitions between usually a copper target element, so that when an electron drops down from a 2p level into a vacancy in the 1s level, you have a 2p to 1s electronic transition, and the energy that is released during that electronic transition is as an emitted X-ray beam. And so the X-ray wavelength, which is about 1.54 angstroms from the copper K alpha X-ray beam, depends exactly on the energy difference between the 2p and the 1s levels. So that's how X-rays are generated, by the transition from an electron dropping from the 2p level down into the 1s level. So that's an emission process, X-ray emission, which in fact is the basis of X-ray emission in electron microscopy. When we do quantitative electron microscopy, doing EDAX, for example, or electron microprobe, that's what we measure. We measure the emitted X-rays, and from their wavelength we can determine what elements are present. Well, the ZANES technique is the mirror image of X-ray emission. That is, it's X-ray absorption. And so using our synchrotron in the national facilities, there's usually only 1 or 2 synchrotrons in any particular country, what you do is bombard your sample with high energy radiation with variable wavelength, and you observe the opposite process of the transition from 1s to 2p levels. You can also observe other transitions from 2s to 3p and so on, but we'll just look at the 1s to 2p transition, and that is called the K edge. And what you can do with the ZANES technique is to measure the exact energy of absorption associated with the K edge. And it turns out that at precise measurements, the K edge absorption depends upon the oxidation state. And what this graph here shows our lithium manganese nickel oxide spinel, and part of the X-ray absorption spectrum in the region of the manganese absorption edge. And the points to notice are that A, B, and C are the absorption edge spectra for 3 standard samples. A is for manganese oxide MnO containing manganese 2+, B is for Mn2O3 containing manganese 3+, and C is for MnO2 containing manganese 4+. And so if you have your unknown sample, measure its K absorption edge, you can get a pretty good idea of the oxidation state of manganese in your sample. And from the graph here, it's rather busy, a lot of data on it. The point to note is that the HOP sample, high oxygen pressure, fully oxygenated sample with crosses as data points, matches pretty well the curve for MnO2. And so we can conclude that the fully oxygenated sample contains tetravalent manganese, whereas the samples quenched from higher temperatures have a reduction in oxidation state of manganese. And so the one quenched from 1000 degrees C matches pretty well curve B, and therefore corresponds largely to manganese 3+. And so there's quite a nice correlation there between quench temperature and average oxidation state of manganese. And so it's a very nice, sensitive way to determine oxidation states. Of course, it's not something that everyone can have in their laboratory, but if you can get access to national facilities in your own country or elsewhere, this can be a very useful technique. And using techniques such as this, the next slide just shows some examples of oxidation states in some of the cathodes. We don't need to go through them in detail. These are for lithium, manganese, nickel materials. The first one is a layered rock salt, and the second one is a spinel. And you can see there that depending upon the oxygen content, the manganese oxidation state is the one that mainly changes in each case, with depending on the material, the nickel oxidation state may be close to 3 or close to 2. So as well as doing measurements on materials themselves, this is also then very useful as a way of studying the changes in the cathode during charge-discharge of a battery. It's possible to assemble a cell in which you can do the charge-discharge experiment at the same time as you can measure the X-ray absorption spectra of the materials, and then that can tell you which element is undergoing oxidation and reduction during battery operation. So that gives very useful scientific information on battery operation. So that's a little bit about materials and how we can characterize them as cathodes. Next topic is to look briefly at anodes. So from our earlier graph on the anodes and cathodes against the cell voltage against capacity, we had data for lithium metal and the lithium graphite composite, and we said a little bit about lithium tin alloys. We can also use lithium aluminium alloys, and these are good from the point of view that their voltage is very close to that of pure lithium, and so these give high voltage anode materials in high capacity batteries. One of the big features of lithium, though, is that when you assemble a lithium battery, during the first charge-discharge cycle, there is a chemical reaction between lithium and the organic solvent in the electrolyte. Now, this could be a major problem. It could be a disaster. But in fact, it turns out to be very beneficial, because this reaction between lithium and the organic solvent forms a product which is called the solid electrolyte interface. And once that has formed, no further reaction takes place. So effectively, it stabilizes the system. It stabilizes lithium in contact with the electrolyte. And of course, that is vital to long-term stability and performance of your battery. You don't want the components reacting irreversibly with each other. So formation of the solid electrolyte interface is good news because it stabilizes the system, but it is bad news because a certain amount of the lithium is lost from the system by reacting with the organic component of the electrolyte. So that's one disadvantage, and in some cases the solid electrolyte interface contributes an extra resistance to the overall resistance of the cell, and so that can have an effect on the capacity and performance of the cell. So this is a general feature, the SEI, of many lithium battery systems. Another anode which is of considerable interest is this oxide Li4Ti5012, which has a spinel structure, because it's possible to intercalate 3 lithiums into this spinel, taking the formula up to Li7Ti5012. And if you calculate the charges on titanium in those cases, in the initial state, Li4Ti5012, we've got titanium 4+ for charge balance, whereas in the charged state with Li7Ti5012, we've got a mixture of 4+ and 3+. So in the charged state, this is where it can be used as an anode and as a source of lithium. It has a disadvantage that the capacity is not high. So if you go back to the diagram showing the capacities of the various anode and cathode materials, you'll find that this lithium spinel is on the left-hand side, so it's not a high capacity anode, but it has some big advantages. One of which is that it's a 3-dimensional crystal structure. It's not a layered structure, it's a 3-dimensional structure. The lithium ions can diffuse through channels in 3 dimensions, and most importantly, there is no major change in volume of the crystal structure during the intercalation process, because the structure is built of a framework of corner sharing and edge sharing tetrahedra and octahedra, and so that's a pretty rigid framework, and so you can put lithium ions into and take them out of the structure, and there's little volume change when that happens. And this is a serious advantage in lithium batteries, because one of the major problems is disintegration of the electrode-electrolyte interface, if you have an electrode in which there are large volume changes during charge and discharge, because this causes a fragmentation of the nice interface between electrode and electrolyte. So the small volume change is a big advantage in such cases. Another disadvantage is that the voltage is considerably lower. So if you look at that chart again, I think this one is round about 2 volts, utilizing this as an anode. But another advantage is that because the voltage is significantly different from that of pure lithium, during charging, the lithium ions go into the lithium titanate spinel, which means that they don't form dendrites. They don't grow as dendrites on the surface. And so that is a good safety aspect of this material. So that's one example, one example of a complex oxide that can be used as an anode. The next slide is looking at battery performance. So one of the big questions in operation of a battery, and especially when it's used to power your mobile phones and laptops and so on, is that you want a constant voltage output. You don't want it to vary during discharge. And so we have a schematic example here of using lithium iron phosphate as our cathode. It is just an example. It's not particularly important, but it is used commercially, lithium iron phosphate as a cathode. And in the charge state, you have FePO4 containing Fe3+, and during discharge, lithium ions and electrons intercalate into the structure. It's a so-called olivine crystal structure to give LiX FePO4. And so the redox couple, the active couple, is iron, and it goes from Fe3+ to Fe2+ on discharge. So the next diagram in the middle shows the voltage profile. And this has a good profile because you have a constant voltage over much of the discharge part. But there is initial drop in voltage, and then there's this constant voltage until the thing is almost completely discharged, and then it drops off again. And so the question here is, why do we get a constant voltage plateau? Because in other materials you don't see a constant voltage. You see a gradual decline in voltage during discharge. So we want these constant voltage regions. And basically the voltage profile depends on whether the intercalation product is compositionally homogeneous, because we want to have a constant voltage plateau. And the question is, does the composition LiX FePO4 change continuously and homogeneously during discharge or not? And perhaps surprisingly, until you think about it, you don't want a gradual change in composition. What you want to have is a two-phase region in which you start off with FePO4 in the charge state and then form LiFePO4 product. But you don't have regions where you've got a uniform distribution of less than 1 lithium per formula unit of FePO4. And that is illustrated at the bottom there, where you have the discharged product and the charged product and the charge state without intermediate states. And this is because the voltage And this goes back to our table of electrode potentials. The electrode potential of a half reaction and an overall reaction doesn't depend upon the amount of that product. It's a constant value. But we saw in the case of oxygen that if you have different reactions and different products, then your cell voltage may vary. And this is what happens in solid state materials. If you have a clearly defined product and then you're simply changing the amount of that product compared with the starting material, your voltage stays constant. But if the composition of your product is gradually changing, then your cell voltage will gradually change also. And so this is really quite a critical thing about battery performance and achieving a constant voltage performance. It's the nanostructure of the intermediate state during the charge-discharge process. And we talk about concentration polarization. So the next slide indicates this, that as lithium ions are inserted initially near the electrode-electrolyte interface, there's a high concentration of lithium ions, but then this decreases rapidly as we move further into the electrode material. And as we've seen earlier, the rate limiting steps depend upon ion diffusion in the cathodes and in the electrode and electrolyte, as well as the electronic conduction. So that ends this part. There's one more small section to consider, and there are some possible future developments. So that will be our final session. So we'll have another break now.